Okay, sorry for the advertisement. And now I want to go from the basics, and eventually we will understand what a quantum computer is about. So quantum computing, in summary, I will say that it uses two important phenomena: superposition and entanglement. We use quantum mechanics in transistor already. That's why we have band structure, electron hole conduction, etc. But quantum computing, it uses two important phenomena: superposition and entanglement, which we will discuss later. And one more important thing is I want to emphasize interference is very important, because without interference, most of the time we cannot get the answer that we want. You will see that later. There are two types of major quantum computing architecture, or paradigm. One is the gate-based that we will talk in this talk. It's just like the gate circuit. We have a classical logic, but not exactly the same. However, we can think in this way for now, right? You have a state and you keep processing by using different gates. Another is quantum annealing. This is basically like to solve some optimization problem. You form an energy landscape by using the quantum hardware or qubit, and hopefully you can find the minimum energy quickly, much faster than the classical one, because it allows some quantum tunneling in the hyperspace or the configuration space that they have. And this is something, for example, the D-Wave has been doing, right? And we heard about very many good things about quantum computing. Yes, if it works, you can help you to design battery, design the drug, even do computational dynamics. Yeah, it provides secure communication. We can use it for quantum machine learning or financial service and predictions. So its economical impact is going to be enormous if it is successful. So what is quantum computing? I would say let's look at the classical computing first. We use 0 and 1 to represent the information. How do we represent 0 and 1? You can use the coin, head and tail, or even happy and sad, a transistor, on and off, right? So it represents the information by the state. Actually, it is the same in quantum computing. But it has something more basic called basis state. It's just like the X hat, Y hat, and Z hat on our 3D space. So using the same token, I can represent the basis state maybe by head and tail, happy and sad, transistor being on and off. And there's no difference between quantum computing and classical computing if you limit the quantum computer to only operate on its basis state. Particularly here, I put a so-called bracket notation. It is nothing but just a notation. So just accept it, right? So I represent a state by putting it in this bracket. What's so special about quantum computing is that it also works on superposition. It means that besides the basis state, I can also have a state which is a linear combination of the basis state. For example, a state psi can be a linear combination of 0 and 1, where 0 and 1 are just the basis state. And to describe this state, for this so-called 1 qubit, I need two complex numbers, alpha and beta. Some people would like to make an analogy like this. The superposition is just like a coin that is spinning on your table. You still don't know whether it's head and tail. And it's a superposition of head and tail. Of course, this is just an analogy. You cannot build a quantum computing by using some spinning coins, right? So what's so important is this. On the left, I'm showing you that in a classical register, let's say in this example, I have 4 bits. These 4 bits can represent 16 possible states. And these are just the basis states in a quantum computer. So if I have 4 qubits, I can represent 16 basis state. So nothing special. But if I have 4 qubits, I can also represent the states of the linear combination of this 16 basis state. That means I need 16 complex number to describe one of the states in this quantum computer register. Now, what if I have n qubits? If I have n qubits, then I have 2 to the power n basis state. And to describe one state, I need 2 to the power n complex number. Maybe a lot of math, but the point I'm trying to point out is that there's a lot of information in the superposition. Think about that. If I have 300 electrons, then it means I have 2 to the power 300 basis states in order to describe these 300 electrons. Then I need to have 10 to the power 90 complex coefficient to describe it. Just to describe one of the states of these 300 electrons, I would not be able to save it in any of the storage we have in this world. There are only less than 10 to the power 82 atoms in the universe. If we can encode one complex number in one atom, we cannot even encode the states of 300 electrons by using all the atoms in the universe. Needless to say, to store in all the storage that we have in the world. So this one did not tell you much, but at least it tells you that the quantum mechanics is very enormous. By just having 300 electrons, it contains a lot of information. That is the power of superposition. Well, then what can we do with that? Well, in principle, quantum mechanics is linear. So you apply a function to a superposition, it will be applied to each of these basis states simultaneously, right? This is kind of a hand-waving argument, but looks like correct. It's just like I have a parallel universe. I have many parallel universes. Each of them try to compute the function for me for each basis state. If this works, that will achieve a very important quantum parallelism. Okay. So we see its power. Then one important thing about quantum computing is how we do the measurement. I told you that a superposition state is just like a spinning coin. How will you measure the coin? Well, I will just stop it, right? What will happen? It may either collapse to head or it can collapse to tail. That is the same for a quantum superposition state. If it is alpha 0 plus beta 1, if I do a measurement, it may collapse to 0 or collapse to 1. So this is completely random. The only thing that's not completely random is that the probability that it will collapse to 0 depends on the square of the magnitude of the coefficient, like alpha square in front of for 0 and beta square for 1. So you see that even I have a lot of information stored in a quantum state, I am not able to get what they are. I need to do a lot of measurement and only to know that what their magnitudes or their relative magnitudes are, right? So this is one limitation of quantum mechanics. But we will discuss this later. So we talk about superposition. We see it is powerful. You can do quantum parallelism, but it's limited by the measurement. We need to deal with that. Another important thing about quantum computing is the entangled state. Now, just now I told you that if you have 1 qubit, you have 2 basis states, 0 and 1. If you have 2 qubit, you can have 0, 0, 0, 1, 1, 0, and 1, 1. Just like the 4 qubit case, you can have 0 all the way to 15. Now here I'm showing you a 2 qubit state which form as a superposition of its basis states, right? So is alpha, beta, gamma, or its coefficient here are half, negative half, half, negative half. For this 2 qubit state that may come from 2 electrons, I can do a so-called tensor products to factorize it into 2 states. So basically what it is talking about is that I can describe this whole system by describing the individual system separately and then combine them. So they are unentangled. Just like before my wife and I marry, we can describe ourselves separately, and then as 2 people, we are not coupling to each other, right? Now, if you have there are some states you can never factorize it so that it becomes the tensor product of 2 systems. In order to describe this system, you cannot describe it from the subsystem. You need to describe this as a whole. This is called entangled state. They are coupled. So this is a very important property in quantum computing. And let's take a look at some special implication. For example, if I create two electrons, I entangle them. I make them in an entangled state. In this particular case, it is spin up, and spin down, spin down. I told you earlier, this is bracket notation. It's nothing but just a notation. Inside it, I can put anything. So this can also be described as 0, 0 plus 1, 1. Or in English, spin up, spin down, down. It's all up to you, right? But we know that it represents the basic state of this whole system, which is 0, 0, and 1, 1. Now, I do it very carefully and move one of the electrons to 100 light years away so that they are still entangled, right? Unless they got disrupted by some external environment, you can imagine they are still entangled, right? Now, what happens if I do a measurement on the electron on Earth? Now, based on this combination, you see that it will collapse to either spin up or spin down. That's what we just said earlier, right? Any superposition state will collapse to the basic state. So for the electron on the Earth, you will collapse to be up or down with 50% because of the coefficient. So let's say I get up. Now, if I get it collapse to up, what will happen to the another electron 100 light years away? In this whole system, when it only has two basic states that has non-zero coefficient. So the whole system needs to collapse to up, or down, down. It doesn't have up, down. So if my electron on the Earth collapse to up, the electron very far away must collapse to up also. So this becomes something called spooky action for Albert Einstein. He said, how the electron 100 light years away know what happened to the electron in Earth instantaneously? Are they transmitting some information faster than the speed of light? We won't go into the details. It won't, right? But this is just to show you the power or the specialty of this quantum entanglement. But I just want you to remember something called quantum entanglement, that these two states are highly correlated. Okay, so we look over the basics of the most important thing about quantum computing. Again, superposition and entanglement and measurement, right? So what is a quantum gate then? Quantum gate is nothing but just rotates the vector in its hyperspace. Again, every quantum qubit or a group of qubit or a register, they are just a state, right? And this state is a linear combination of the basic states. When you apply a gate to it, you rotate it in the hyperspace, not in the space we live in, but in a hyperspace, mathematical hyperspace. And people like to map it to something called broad sphere when it is 1 qubit. We won't go into detail, but this broad sphere is something sometimes pretty useful, but sometimes can be confusing. But anyway, for example, when you have a 0 state for this qubit, you apply a gate, you can rotate to any part on this broad sphere and it becomes a new state. How do we rotate it? Very often, a gate is just a laser or microwave pulse. It's not the NOT gate or a LAN gate we lay out on a semiconductor chip, right? We will discuss more later about that, but remember this. There are different types of gates. Some of them has classical counterpart. For example, the NOT gate. The NOT gate, what it does is just change the basic states from 0 to 1 and 1 to 0. It also has two qubit gate. For example, a control NOT gate. So what does it do? It is going to change the second qubit, or what we call the target qubit, from 0 to 1 or 1 to 0. That means apply a NOT gate to it if the first qubit or the control qubit is 1. If the first qubit is 0, then it's not going to do anything to the second qubit. Okay, but we can build this on a classical computer. So nothing special, as I told you before. Quantum computing is the same as classical computing if you limit them to only operate on the basic state. If you don't allow them to work on superposition, it's not going to be useful. But it has some gates that has no classical counterparts. For example, a Hadamard gate. I have a basic state start from 0. After I apply the Hadamard gate, it becomes a superposition of 0 and 1. In classical computer, if you have a register, I ask you what is the content, you say is 0 or 1, fine. If you say 0 plus 1, we know that this is an error. It must be an error, right? But we can do this in quantum computer. So let's take a look at the control NOT gate or exclusive OR gate. This is a very important gate to do the entanglement. There are some so-called universal sets of quantum gates. A group of 1 qubit gates, which is easy to implement, and then a few of the entanglement gates. And one of the important one is the CNOT gate. If you have the CNOT gates, 2 qubit gates, plus this 1 qubit gate, you basically can build any algorithm from scratch. So let's take a look what I said earlier. I said that you have 2 qubits. One of them is control qubit, the second is target qubit. When the control qubit is 0, you do nothing to the second qubit. You see that? So it is still 0, 0, 0, 1. But if your control qubit is 1, you negate the second qubit. So 1, 0 becomes 1, 1, 1, 1 becomes 1, 0. And here shows a circuit that we usually draw. We won't go into details, but I want to remind you that in the future, when we read any papers or textbook, make sure that what they mean by the most significant bits and least significant bits in their circuit. In this particular case, I put the most significant bits on top. So top is the control qubit, the bottom is the target qubit. Because of this, its effect on a general 2 qubit state, right? Because I have 4 basis states, right? And 4 coefficients, right? Is to swap the coefficient of these 2 basis states. Okay? Let's take an example, look at an example how it does the entanglement. I can start with the ground state. So I have 0, 0. I go for a Hadamard gate. Remember, I just told you Hadamard gate is the one that can create superposition. So 0, and I only apply to qubit A, the most significant bit, right? So B doesn't change, but the A becomes a superposition of it. And then just like what we do in elementary school, do this distribution law. This is called tensor product. We don't go into the detail, but they have this, they share the same math. Then you get 0, 0, and 1, 0. See the superposition of 2 basis states of this whole system, right? Remember, what is the basis state of this whole system? It's 2 qubits, so we have 0, 0, 0, 1, 1, 0, and 1, 1. In this case, it only has 0, 0, and 1, 0 component. And then I apply a control NOT gate. Control NOT gate say that if the first qubit is 0, do nothing. So 0, 0 is still 0, 0. If the first qubit is 1, negate the second qubit, then I get 1, 1. And this is the entanglement states I showed you earlier in the spooky action slide, right? Spin up, up, spin down, down. So up to here, I show you the basics of some qubit and the entanglement gate. And now let's go up to a higher level to understand what quantum gates and circuits are about. One important property is that quantum gates are reversible. For example, in the classical computing, I give you the gate type and also the output. You don't know what the input is because 0, 0, 0, 1 and 1, 1, 0 for an AND gate, but all give me 1, 1 as the output. So it's not reversible. But quantum gates must be reversible, as you can see here. And that is just because of the physics of quantum mechanics. I told you earlier what is a quantum gate. It is just a laser pulse, a microwave pulse. You apply to a qubit, you change its state. So this is follow the Schrödinger equation. So you rotate it in the hyperspace, so you can rotate in one direction. You should be able to reverse it in another direction. So here shows usually what we see, a layout of a quantum circuit. And now I want to tell you what is different from the classical circuit. I start with a state. This is a state, later I will show you, in a qubit, for example, a transmon qubit. We apply a gate, it means we apply a microwave pulse. It doesn't go through a gate like the LAN gate nor gates on our IC layout. We apply a pulse to it, it rotates its state. Apply another gate means another pulse, rotate its state again. We apply N pulse and then do measurement. In this process, they are reversible, as I said, right? You apply a pulse to rotate to that direction. I can apply another pulse to rotate it to another direction in their hyperspace, not in our 3D space. But after we do the measurement, we cannot go back. Now, do you see that this is the flow of time, not a space? So in some algorithm you see in the future, they say that you need to apply 1 billion of gates. You will get very nervous if you are IC layout designer. Well, I need to apply 1 billion gates. That is impossible or difficult in an IC chip, right? In a train. But here just means that you keep applying the same different microwave pulse 100 times, 1 million times, or 1 billion times. Okay. The last topic of the part one, what I talk about is about error correction. Now, in classical computer, usually we will do duplication to avoid the error, right? I call my mom in Asia and I say something to her she cannot hear. I keep repeating 100 times. At least maybe 50 times she heard that. Then she get that as the answer. But in quantum computing, it doesn't work because there's something called no cloning theorem. You cannot copy an arbitrary state. Okay, so then what can we do? One of the method is called so-called syndrome measurement. Just like some medicine or traditional medicine, like they don't really test what you have. They look at the syndrome, right? If I'm coughing, I don't know if I got COVID or just regular flu. I went to the doctor. One possibility, instead of testing my blood or my saliva, maybe the doctor is so experienced, say, how often does you cough? What's your fever? Hearing to my heartbeat, and then maybe the doctor came up with a conclusion, oh, you just have a regular flu. That is what we do in quantum computer also for error correction. Psi is a state that I care about. What I do is apply some CNOT gate to entanglement to some auxiliary qubit. And then maybe I got some error. This is just a gate to mimic the error. Through this, I can just measure this gate and then do appropriate operation to psi based on my measurement outcome. So here, not just that we have measurement. This circuit is just that you do the automatic correction. Let's take a look at, on an example. Again, I said the psi is what I care about. And then it is in terms of alpha 0 plus beta 1. I don't know what is alpha. I don't know what is beta. Right? Again, this is 1 qubit, right? Because I have 2 basis states, 0 and 1, and 2 coefficients. So what I do is combine with this auxiliary qubit starting with 0. So what is the basis state of this whole system? Because these two are 0, so I only have 0, 0, 0, and 1, 0, 0, right? I have 3 qubits, I have 8 basis states. Remember? 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, all the way to 1, 1, 1, right? But because these are 0, so the whole system combined with psi is just 0, 0, 0, and 1, 0, 0. Then I go through the first control NOT gate and the second control NOT gate. Again, control NOT gate says that if this is 1, negate it. If this is 1, negate it. For the first basis state, this is 0, nothing changed. For the second one, this is 1, right? So I change 0, 0 to 1, 1. So you see it's entangled. That's why we say this is a process of entanglement, which is very important. Let's say I'm very unlucky. I got the first bit flipped. It was 1, 0, 0, 1, now becomes 1, 0. It's flipped, right? So this circuit will save me. Why? Now, I have another control NOT gate. It says that if this is 1, flip it, negate it. If this is 1, negate this one. So look at this. This is 1, right? Because it got flipped. So it's going to negate 0 and 0. So I got 1, 1, 1. The second one is 0 here. Then I'm not going to do anything because it's the property of control NOT. So I still get 0, 1, 1. Right? So with this, then what happened at the end? How do I correct? With this circuit, this is a so-called control NOT. We did not discuss. It means that I'm going to negate this bit if both of these are 1. Now look at this. Both of these are 1. So here, both are 1, so I'm going to change back to 0. Both are 1, I change this to 1. And you see that through this operation, I recover psi equal to alpha 0 plus beta 1 because I don't care of this auxiliary bit. So in quantum computing algorithm, very often you will see the so-called auxiliary bit or ancillary bit. They're critical for the operation, but you discard them at the end. Okay. Try different type of flipping, right? They can also flip your auxiliary bit. You will find that you can correct that. Okay, at this moment, I would like to just show quickly an algorithm which is called Deutsch algorithm, and just so that you have an idea on what it is about, right? So Deutsch algorithm is something that help you to answer a question. I have a function, a black box. Right? This black box actually can be very complicated. For example, I always think from IC perspective, does this circuit pass the timing criteria, right? When you take our IC, 10 billion transistor or 1 billion transistor, do you meet the timing criteria? This is yes and no question. But to answer this question is super difficult, right? So here is a simple question, very simple. Just, a simple example. It only takes one bit 0 and 1 and output 0 and 1. I want to ask whether this function is constant or it is balanced. Constant means whatever I put in, it gives me the same output. For example, constantly 0 or constantly 1. Balance means that whatever I put in, it always gives me, not whatever, but for all the vector I put in, it will give me half 0 and half 1 as the output, and that is called balance. Now in classical computing, if you don't know what the function is, what do you need to do? For this simple question, you need at least 2 computation, right? Okay, I have some video for this you can learn, which is in the video that I showed you earlier, right? You need at least 2 computation. But for quantum computing, I only need 1 computation by utilizing the quantum parallelism, okay? And the way we do it is to encode the problem into something called quantum oracle, which is one of the most difficult problem because very often people come up with a quantum algorithm. The problem is difficult to implement the quantum oracle. Let's say we can implement, but a quantum oracle, again, is just like a huge quantum gate. It's a gate, a complicated gate. But it still just tell me when I have input xy can be 0 and 1, what the output will be. You see the output is that x is going to keep constant, just like a control NOT gate. But the output, the second qubits, the target qubits will become y exclusive f of x. So you see that the information of f is encoded in the quantum oracle. But what is f of x? You also see that this oracle cannot tell you because it only give you y exclusive f of x, not f of x. So we actually are missing some information in order to get this answer. The overall result is that I can find out whether it is balanced or constant much faster by only using 1 computation. And it's the same if it turns out that we have many qubits, also only 1 computation. But I don't know what the function is. I don't know when I input 0, it is going to give me 0 or 1. Okay? So this is the flow of the algorithm. Again, this you don't know this if you did not study before. I just want to show you, let you appreciate how people construct the algorithm and what are the critical parts on an algorithm. And most of the algorithms are pretty similar. First, you need to have the quantum oracle. As I just told you, you need to encode this f of x into the oracle so that it has this relationship. There are other types of oracle, of course. Another thing is I'm going to prepare this in a superposition. I hope you ring the bell. I prepare it in superposition because I want to do quantum parallelism. I want to have all these states at the same time. And then I apply to this oracle, then it will compute at the same time. Now, as I told you earlier, I cannot get the coefficient fast, right? Because I need to do measurement many times just to know its relative magnitude. So I need to do some special operation, which basically is just constructive and destructive interference. So that in this case, it always gives me 0 at the output if the function is constant. And it always gives me 1 if the function is balanced. Okay, and that is how Dodge algorithm is constructed. Okay, so let me do a quick live demo. I don't want to waste you. Can you see my screen?
Yes, we can still see it.
Yeah. So it's called IBMQ. I already have my account, right? It has two things. One is called Lab Composer. One is called Launch Lab, right? Composer is the GUI interface. It's simpler, so we'll do this. The lab, you can use the Python programming to run it, okay? So I come to here. This is, you see the interface. You see, probably you already see some of the gates already, right? That you can recognize some of them, right? And I need to take a look at my cheat sheet, right? So just, I'm going to have 2 qubits. So maybe what I'm going to do is just right click, just click left click, delete those that I don't want, right? And then I'm going to apply NOT gate to this and an identity gate. Identity gate means I'm not doing anything. NOT gate just makes 0 to 1 and 1 to 0. And after that, I put 2 Hadamard gates. The reason is that I want to create a superposition. I add this breaker just to make it nice. This has no function. And after that, I need to put the quantum oracle. Now here I put a very simple quantum oracle, which is just corresponds to the a constant function when all the output are 0, right? So I don't go into detail to prove that this fulfill that, but this is just for a simulation purpose, demonstration purpose. In reality, of course, you don't know what it's difficult to construct the oracle, right? It can take a lot of time to construct. Then your algorithm won't be useful. Then I apply a Hadamard gate, as I say, to do the interference, and then eventually I will do a measurement. Right. So I'm not showing the slide, but I said earlier, if this is a constant function, then I expect the output to be always 0. Okay. Now here it has 4 classical registers. This is just a register to store your output. So originally it has 4 qubits, that's why it has 4. So I'm going to reduce it to 2 because I only have 2 registers, right? And then what do? I will just submit the, I will just go here, set up and run. Now it does have many real quantum computer, but nowadays it takes a long time. Sometimes take 1 or 2 hours, even longer. So I will just submit to a simulator. This is basically just a emulator using classical computer, right? So I just click on this and then I submit the job. So it may take some time. I don't know what will happen. So maybe I will just show you what I had set up and run, right? Okay, it has new job result already. This is fast, right? Just so I click on this. It takes some time to load. Just bear with me. If it doesn't work in 30 seconds, then I will open my old result. Okay, so it has the results. I do want to show you something so you have a better understanding about the quantum computer. Let me see. Oh, okay. Yeah, anyway, I will show you later in another example because this is simulation. I cannot show you that. Now, this is the measurement outcome. You see, it is all 0, right? Then we know that this function is balanced. Actually, what I want to show you is the job that I ran with the real quantum computer. Unfortunately, I cannot find it. But basically, what I want to tell you is that it will go through a compilation process. So what you are doing here is just a gate, but then it will further compile it to something with higher fidelity, so that it a more primitive gate, or you can say more primitive gate, so that you have a higher fidelity. Okay. So I will stop here and go back. Can you see it? Now I'm on the presentation mode. What did we learn? Can you see it?
Yes,
Okay.
I can see the slides.
Thank you. Yeah, so basically, I already said what we have said. We need to encode in the quantum oracle. But this is information, something I want to say. Quantum computer is not really something very unbelievable. Right? In this example, we see that, yeah, I can get the answer quick, but it doesn't mean that I get all the answer I want. It is, I feel that it has something like conservation of information for the time you can spend. What we are doing, just we give up the details of the function so that we know that which is 0 and 1, right? So I feel that it just show us another path to find the answer. But this is just a hand waving. Maybe the mathematician can prove that I'm wrong. They really have a real proof that saying that the information we can get from there is much more than the classical computer. But the most important thing, I do want you to understand there's a trade-off of the information. Okay. So I'm done with this.
Let's go on.
Yeah, so we have learned the basics. The algorithm looks very fancy, right? If they work, but how do we implement in hardware? There are many different hardware. So first we look at this divisional criteria. What hardware can be used to make a quantum computer? First, you need to have a well-characterized qubit. Basically, what it's saying is that your qubit need to have two basis states, 0 and 1. Do not give me more. Because all the physical system, they can have multiple qubits. They can have 0, 1, 2, 3, 4, 5 different states. If that happens, you are operating in a higher dimension, more profound qubit space, and you leak the information to another space, right? Then it won't work. Of course, you can say you formalize your quantum computer to work on 4 level. That is also okay. Just like classical semiconductor, or logic. Right now we're 0 and 1. We do have multi-level logic, like even the flash memory. They have they can store 0 to 7, 8 states, or even more for 1 bit, right? So, but if we say that only 0 and 1, then you better have a system that won't lead to higher states, because that will cause error. You need to be able to initialize them quickly. If you just take a look at the algorithm I just showed you, we initialize it to 0, for example, 0 at the beginning. And that is the best way to start the quantum algorithm. Okay, and so you should be able to initialize it. If your system is going to take 1 minute to initialize a qubit, it's not going to work, because there are many algorithms you want to initialize it very frequently and many times. And also, for like last time we say, we need to run many times to get the answer. So you need to run it initialize many times, and then you will have a problem, right? Long coherence times. When you are at 0, you better stay at 0. At 1, stay at 1. Do not change to other state before I finish the computation. So you want to have a coherence times longer than the gate time, right? You definitely should be able to do 1 qubit gates and entanglement gates. With this, then you can do most of the algorithms. Another thing is that you should be allow them to measure individual qubit. Sometimes the whole system need to be measured. Then it won't be useful. Just like the spooky action I just mentioned to you, I measure the qubit on the Earth. If your system need to measure every qubit at the same time, it won't work. For example, something called quantum teleportation will not work if you need to measure them all at once. If you want to use quantum communication, you also need to make sure that the qubit is flying, so need to be able to interact with the stationary qubit. And also, when you are flying, you need to be keep the coherence, right? But we are only talking about quantum computer here. So how do we implement the qubit? Well, as a joke, it can be a superposition of happy and sad. You ask me, how's my mood today? I may say, oh, kind of happy, kind of sad, right? But not reliable. In reality, what we can do is, how about spin qubit? It can be spin up, spin down. Then they have two different energy level in this quantum dot. And then you can form a superposition of these two qubits. You can also use photonic. This is just a waveguide, and I did not draw it. You shoot a photon, one single photon, and they are symmetric. So where is the photon? In quantum mechanics, it is a superposition of these two paths. It can on the top and the bottom path. That is the superposition. But when you measure it, you can only find it either here or here. You cannot find it at both, right? Because I only have one photon. That is the collapse of the wave function. The one that we are going to talk about is the superconducting charge qubit. This is something called Josephson junction. Josephson junction is just like an LC tank. If I add a capacitor in large enough capacitor, it also has its parasitic capacitor. It's just like an LC tank, but it has non-linear inductance. Because it's non-linear, that solves the problem of equal spacing of different levels in a simple harmonic oscillator. I just told you that to be a quantum computer, you need to confine it between 0 and 1 state. You cannot lead to second state. So if we have different spacings, then we can confine it in 0 and 1. And what it does is this. It has a capacitor here. This forms an island. In this island, you can have 0 or 1 extra pair of Cooper pairs. Cooper pairs is a pair of electrons that occurs at superconducting state, right? We don't need to go into that details, but it's just a pair of electrons. They work together. So treat it as a new particle. So I have 1 extra or 0 extra particle here. That represents a qubit. And of course, it can be a superposition because it's quantum mechanics. I have a linear combination of 0 extra and 1 extra Cooper pair. Okay? Now, both, no matter what you use to implement, maybe not for photonics, they only have very small energy difference between the 0 and 1 state. And because they interact with the outside world, they can lose their state due to decoherence. On the right, I'm showing you the scale of energy scale as a function of temperature. For example, at 300 Kelvin, it's about 26 millivolts of thermal energy. We can cool it down by liquid helium to 4 Kelvin, but a qubit separation is only in the order of 0.02 millikelvin, very small. It's equivalent to 0.3. So sorry, I say the wrong thing. The energy is 0.02 milli eV, right? Correspond to 0.23 Kelvin. In order to make it work, we need to cool it down so that the environment is cool enough. For example, in dilution refrigerator, in the order of 10 millikelvin. Then you have the thermal energy at least 10 times less than the qubit separation, so that you won't be affected by the thermal energy, so you have a longer coherence time. You can use dilution refrigerator, DR, or laser cooling, for example, in the trapped ion. So what is the coherence? For example, I may be in the 1 state, and I try to wait for different time. So here this is a real superconducting quantum computer experiment. We did in Livermore National Lab. When you wait for a long time, when you measure it again, you say that it starts decaying to 0. The probability of finding 1 becomes less and less. This is so-called T1 coherence time, only in the order of 219 microseconds. So you can imagine your gates need to operate way faster than that, maybe 0.5 microsecond, so that you can have enough operation before it decay. Okay. Another thing is the so-called T2 decoherence time. It is saying that I start with a superposition. It is still in superposition, but it loses the phase gradually. Usually it is much shorter than the T1 time. As this is oscillation, I don't want to have time to go into detail, but that is the way to measure the T2. We bring it to the superposition and then rotate it back to non-superposition and measure the 0 and 1 states. It will oscillate. But anyway, the envelope determines its decoherence time, right? So you need to be less than T2 because T1 and T2 are all there at the same time. So you need to be much less than T2 for your qubit to work. So I just told you, we can actually use the LC tank to make a qubit, right? If you do some quantization, right, circuit quantization, you will find that it behaves like a simple harmonic oscillator. You have 0 extra electron, 1 extra electron, 2 extra, photon. 0 extra photon, 1 extra photon, 2 extra photon. You may feel surprising why you're talking about photon. Remember, electromagnetic wave. Photons are electromagnetic waves. That's why we call it photon, right? So everything is governed by Maxwell equation. So 0, 1, 2 photon in this LC10. The problem is that they have equal spacing. So we say that lack of anharmonicity. When you have equal spacing, then apply a pulse, you go to 1, apply another pulse, you won't go back to 0 because you may go to 2, then screw up. That's why we use the simple harmonic, use the Josephson junction. Here is something called transmon. We have a parallel capacitor. In this case, you see the energy separation becomes smaller and smaller when you go up, right? So I can confine them in the 0 and 1 state. Of course, now this is photon. This is like extra Cooper pair for this qubit, right? And here it has two important quantity. One is so-called the EC, the coupling, the capacitance, the capacitive energy here due to this capacitor. Another is Josephson junction energy. And what is that? Don't worry about the equation. I'm showing you this, just want to show a few important concepts. Josephson junction is a very simple device. A metal, insulator metal, just a capacitor. But because we cool it to very low temperature, it becomes a superconductor, insulator, superconductor. That's it. The special thing about it is that it has a constant current, or its current depends on the phase difference across it. We did not discuss this, so I'm sorry if you don't really get this because it needs a lot of explanation. But there's something called phase for this quantum object, for this Cooper pair. They have a phase because they are the wave function. The phase difference determines how much current going through. And the phase will change if you apply a voltage. So basically, even you have 0 voltage, but you have phase difference, you get current. You don't have this in a regular resistor, right? And that is because they're superconducting. Even you don't have voltage, you expect a constant current keep going through, okay? So that is the so-called Josephson junction equation. And it has nonlinear inductance. That is what we just said. Okay, it depends on the phase. The only message I want you to remember is that its inductance is nonlinear. That's why it makes it a good qubit. It also has the associated energy because it's an inductance, right? An inductor has energy. A capacitor has energy. So that's why we have this EC, capacitive energy, and also EJ, which we call it Josephson junction energy, but which is nothing but just the inductance energy that it has. Here shows the layout of a transformer from this paper. This is the IC layout. You look from the top. Here, the gray one are just the insulator, the substrate sapphire insulator, the substrate just something to hold the device. This very tiny thing you cannot see is the Josephson junction. Aluminum, insulator, aluminum. That's it. They form a junction there. That is the whole Josephson junction. Very simple. But they also have a large capacitor in parallel with it. This is for this structure. I have Josephson junction, I have a parallel capacitor. Because you want to form something called transmon qubit. A transmon qubit has a large shunt capacitor. For some reason, I will explain later. And this is a qubit already. And I said earlier, I don't need to form the gate because I'm going to put the qubit here, and then I have a transmission line going all the way to a port. Then how do I operate on this qubit? I apply a gate pulse. Then the state of this Josephson junction, which is a linear combination of 0 and 1 extra Cooper pair, will change. The alpha and beta will change. And that is how we operate a qubit. Okay. Now this is the chip. But then how about the whole system? Here shows one of the work we did earlier from this paper. Of course, it's not about this term. It's about the study of the readout. But here shows the how a quantum computer is made today. It occupies a whole room, super big. Because first you need to have this server from a company called Quantum Machines. You can have it yourself. What it does is keep generating pulse, very high speed pulse. And based on the readouts, it generates other pulse. This microwave pulse will get to the mixer to bring to the right frequency. And they are at 300 Kelvin. Then we will go through attenuator to filter the noise to make to reduce the thermal noise. Keep going. 300 Kelvin, 4 Kelvin, 700 millikelvin, 10 millikelvin. So this is in the dilution refrigerator I just mentioned. And here we sit a resonator. This is different from this one. It's a 3D resonator, but you see that it's just the same as this circuit. And inside the resonator, it has a very, very tiny qubit that you cannot see here. That is one of the qubits. The pulse we shoot in is negative 47 dBm, very small. When you get attenuation and reach the resonator, you only have about 363 photons, right? If you make it smaller, so they are countable. That's why they are very sensitive to noise. So in this setup, we are showing the readout. We shoot the pulse here, and then we try to read the pulse. And you need a quantum amplifier, which add the least noise to it, and then you have different stages of amplifier to see the signal, right? So you see a quantum computer is really nothing but 99% classical electronics, cryogenic electronics, FPGA, high-speed electronics, control theory, error correction, mechanics, and dilution refrigerator. And only this part is qubit. Okay, so if you're an electrical engineer, you're an engineer, you should consider to go to this field, because without you, quantum computer is not going to work. Okay, so here I want to talk about how we read out the quantum computer. So as an initial introduction, the way we do it is that we shoot the pulse to here. This is a resonator. We were going to detect the pulse. Depends on the resonance frequency. We will have the largest amplitude when the resonance frequency meets our pulse frequency. Okay? But when you have a qubit at 0 and 1 state, it's going to change the resonance frequency of this system. So if it is 1, resonance frequency may shift to lower. When it's 0, it may shift to higher. And that is how we read out the qubit of a superconducting qubit. Because of time, I will just quickly go through this line. Don't worry, because it's impossible to understand if you did not study before. But the message I want to tell you is that there's something called cavity quantum electrodynamics. That's what physics people have been doing. They put an atom here in an optical cavity. This atom has two-level system. And the optical cavity also can contain 1, 0, 2, 3, 4 photons. And they interact with each other. That is the so-called Hamiltonian describing the interaction. But no worry about this. The most important thing is saying that I can excite the atom to a higher level by absorbing a photon. Or the atom will emit another photon by going to a lower level. So that is a cavity that allows us to distinguish the level of this atom by shooting a laser pulse to here, right? So although I did not plan to talk about other quantum mechanical architecture, this is one of the possible qubit that you can do. And it's not, similar to trapped ion, right? So use the atom as a qubit and use the laser pulse to probe it or to manipulate it. There are two frequencies. One is the cavity resonance frequency. One is the atom transition frequency. And they also have the coupling strength between them, right? When the two frequencies are different, we say there is a detuning. And this is important so that when this atom is at different level, it's going to change the resonant frequency of this cavity overall. If they have different, if there's a detuning, then you are going to have a different change of the of this two level. As a result, when your atom is at 0 and 1 state, your overall frequency will shift. This is confusing. I know I did not explain well, but this is just to bring you to our superconducting qubit. I just want you to understand that we lay out the chip, we can lay out a resonator. This is the cavity. Just like the optical cavity here, two lengths here. And it's coupled to a superconducting qubit. This superconducting qubit has two levels, right? 1 or 0 extra Cooper pair. It is just like an artificial atom. So it has two states, 0 and 1. And this level are talking about I have 0, 1, 2, 3 photon. Again, this is electromagnetic wave, so it is photon. Same as optical cavity, but just different wavelength. So I can have a state that have a 0 Cooper pair and then have 0, 1, 2, 3 atoms like this, right? Photons. So I have 0 photon or 0 charge. Or I can have 1 Cooper pair, but 0, 1, 2, 3 photon. So I have 0 photon and 1 charge. How do I know whether it is 0 and 1? And that is what I tried to tell you earlier. The state of the atom is going to change. You see this omega r minus G2 over delta change the level of adding 1 photon to the system. If you have 0 charge or 0 Cooper pair, the energy you need to excite or to include 1 photon to this resonator is omega r minus G squared divided by delta. If you have 1 Cooper pair, it is omega r plus G squared divided by delta. Now, no need to memorize this, right, if you feel confusing. But I do want you to memorize that how it works. It is that the states of your qubit change the resonant frequency of the cavity. That's it. And because of this, the resonant frequency is changed. Now, if I apply a pulse to it, right? Apply a pulse to it, then it's going to have different peak when I measure it. And by doing this, I know whether it is in 0 and 1. So that completes the description of the how we measure a qubit in a superconducting hardware. Here show a simulation in this paper. So but it's a good thing to show how it works. We actually measure at a center frequency. And because all these microwave pulse, they has real and imaginary parts because they have a phase. So whether if you are at 0, you have a different, if you're peak frequency shift lower due to 0 or shift higher due to 1, you have a different real and imaginary part combination. So when you read it at this frequency, right, you will have different so-called IQ block. You have here show you the in-phase and out-of-phase quadrature, but it's just same as real and imaginary. So because of noise, you actually have some distribution. It's not always at the center point. So in quantum computing, what you want to do is to set up the device so the separation is large enough. And then I will say anything above this is 1. Everything below this is 0. Again, what is below this? It means the real and imaginary part has this type of combination. And you see that some of the green comes to here because of the noise. And this constitutes the fidelity of the readout. Okay. So we're almost done. We know how to make the superconducting qubit. We know how to do the readout. Then how do I do a single qubit gate? Here is pretty complicated. No need to understand. But the main point I want you to get is, I showed you the broad sphere earlier. For any single qubit, the state can be mapped to a broad sphere. So every state is on top of the sphere. So what is a quantum gate again? It's the rotation of the vector on the broad sphere for a single qubit, right, in its hyperspace. So basically, we can use something called Euler rotation to make it systematic. You can rotate it 3 times, first about the z-axis, and then about the y-axis, and then about the z-axis for different angle. Then it corresponds to this matrix. You can ignore it. But this matrix is useful for us to construct a physical qubit, right? Everything I want to tell you is that a single qubit gate is the rotation of broad sphere, and by getting the correct matrix, then we know the angle we need to rotate. Now I want to emphasize this rotation is not in our 3D space. We just map the hyperspace to our 3D space. But this rotation does have some meaning correspond to our 3D space because, for example, in a spin qubit, the 3D space, the z direction correspond to the magnetic field direction. But however, still, we are not rotating in the 3D space. Please remember this. So when we implement the superconducting qubit, it is like this. We will apply a gate pulse to here. Now, we can construct the Hamiltonian, which I cannot show here. It's pretty long. Again, it's in the YouTube playlist I showed you earlier, Quantum Computing Architecture we derived from scratch. You will find that no matter it's Hamiltonian, right? That means the equation determine how it change can be expressed as this. And this is just like a spin case. It can be modeled as like I have an effective magnetic field. This is just a mapping. It's not that we have the magnetic field in this system. Okay? But why do I want to show you this equation? I want to show a few things. First is that you will apply the gate pulse with some signal so that you change this Ng, which is a part of the E. You see, E is a function of the capacitive energy and also Ng, which is the background charge. By changing this voltage, I'm going to change the charge here, right? Just capacitive coupling, right? If you are E student, that is easy for you to understand, capacitive coupling. So if I have a smooth pulse here, I'm going to change the Ng here with some small signal, right? Eventually, you find that this Hamiltonian is equal to this. The only thing I want to show you is that this is mapped to a spin qubit. So in a spin qubit, I think you all kind of understand a spin under magnetic field. It will precess, it will rotate about the magnetic field, right? I map this to here, it is the same. It's going to precess and rotate about this broad sphere so that I can get any arbitrary 1 qubit quantum state. And I can move that quantum gate and I can move it to any place, right? But I want to show you, you see, delta depends on Josephson's energy, capacitive energy that we mentioned earlier. This omega depends on eta, which depends on the gate voltage you apply. It also depends on the phase, which is very important. It depends on the phase of your driving pulse. So you see that quantum computing is very delicate. It has a very good control on the pulse that you are sending to the qubit, including its phase, not just its noise from other sources, its frequency, right? And that's why earlier I showed you that people like quantum machines, they just sold this system for a lot of money because they have a lot of FPGA and algorithm and interface to make this easy. Okay. So there is single qubit gate. For example, here we can apply the X and Hadamard gate, and then we can let it oscillate from 0 to 1, 0 to 1, right? Finally, I will talk about the 2 qubit gates. I cannot go too deep, but basically, for example, we talk about CNOT gate, right? But it's not just CNOT gate that is useful. You can also use I swap gates. This is the I swap gate, and for this gate, it is also an entanglement gate. So if you can transform the CNOT gate or other operation to using I swap gate for different quantum computing architecture, you will see people use different entanglement gates because of the physics. We are using the physics to implement it. For example, in a spin qubit case, they actually use the control phase shift gate instead of I swap gate or instead of CNOT gate because it's easier to implement due to physics. In this case, I have 2 qubits, of course, because it's 2 qubit gates. And what they're doing is rely on this coupling of this capacitor. So a hand-waving understanding given by this paper is that you can be 0011, right? Again, what is 0011? It's related to the energy. They have different energy. So if they are both at 0011, just like a classical circuit, they are not going to exchange energy. So the states is not going to oscillate between them. But if one of them is 0, one is 1, then they will start oscillating, right? And this can be seen from this matrix. The first one is correspond to 0, 0. The last is 1, 1, right? If you understand the matrix well, but otherwise this is okay. With this type of oscillation, you just do the time correctly. You want to turn on them so that you change their coupling and also energy difference. It's not shown here, full and other circuit. This oscillation, and then you do the right timing, you can make this to 0. When this is equal pi over 2, this is 0, and this is equal to 1. Right? So again, a very precise control is important. And I guess you will understand why there's so much error, not just the noise, but also the control. Okay, so that's almost the last slide, right? So I try to cover from the basic algorithm all the way to the hardware. I hope you have some idea of what quantum computing is about. I want to say, you see that we are with 100 qubit, 300 qubit, I get a lot of information, but unfortunately, it's in the qubit. I cannot get A0 all the way to A to the power n minus 1. Then what should we do? We need to use constructive and destructive interference or some smart algorithm that use this interference so that it tells us the answer that we want. For example, in the function balance question, or in Shor's algorithm, the period of finding the function, we use this to solve some very difficult problem in classical computing. Okay, quantum computer cannot replace classical computer because they cannot do 100 plus 100 well. It spend a lot of it just cannot, right? Based on what we discussed, but it's a very powerful accelerator, right? So I think you can see high-speed classical computer plus quantum computer, maybe plus ChatGPT, will really revolutionize the world in the future. Okay. Finally, if you're interested to continue to study, my experience is that you just really go through the math and accept them. Okay. Do not think too much philosophically. Right. That's what it was said here in this paper. And finally, again, the advertisement for my book and my YouTube video. you will see a lot of information there. Okay, so